Okay, welcome to the fifth lecture, actually. This is the reading week, so I'm really sorry that I need to replace the lecture 3 to this reading week. So the first thing I want to talk about is actually I've uploaded, it's not the page. So I uploaded the reading week homework as well. Let's see. So let me make it larger. The exercise 5 I have uploaded this week, Tuesday. So later on I actually upload the reading week exercise as well. But I'll give you 2 weeks to finish, so it will be, the deadline will be on 10th of March. So because I see that even exercise 5 has substantial materials, and reading week is just trying to consolidate with you some of the concepts that I've talked about. In particular, you can look at the first question is actually about PACF. So some of the most common mistakes that students may make about the what I talked about on the lecture about PACF. So I basically make them as questions and post it as a reading week exercise. Okay. So and some of the algebra for calculating PACF as well. Okay. So and for this question, so I posed that as a seasonal ARIMA model. So I will try to talk about that today. But the case study is actually an accumulation of your knowledge from previous exercises. So read data, to plot data, and then to transform data. So at the last part of the last lecture, we talked about transformation to remove any trend and seasonality of the data, right? So this actually is a way to test you if you know how to actually do this, okay? And some of the more practical side of it, so I'll actually talk about in this lecture, okay? So let's go to this lecture. Okay. So the first thing I want to talk about is if you remember last time we talked about transformation of data to actually remove trend and seasonality. So we introduce difference and seasonal difference as well. So difference is 1 minus b, the backshift operator, and seasonal difference is 1 minus b to the power s, where s is the known seasonality. So if you ask about unknown seasonality, I'm afraid it's out of scope for this course. So it's basically related to spectral density estimation, which I cut out from this course. So known seasonality, most of the data you actually know seasonality. So if you treat, say, weekly data, if you remember, if you have done the previous exercises, so I have the COVID data, right? COVID data is weekly data. So weekly data, usually you have what? Seasonality of 7 days, basically. So for monthly data, you usually have seasonality of 12 months, okay? So these are actually, usually people will tackle this seasonality first. So for instance, making seasonal difference. But first of all, to see if there indeed are seasonal effects, that is detrimental. Detrimental means it makes the time series not look really non-stationary. Okay, so I hope I've talked to you about the practical side of ACF. Looking at ACF is too many states sticking outside of the blue dotted band, then it may not really be practically stationary time series. Then you consider transformation. So it makes the reading week exercise more important. So in the case study in the London House Prize will actually go through all this. You need to think about how to make transformation, how to actually see why the data is not really stationary. Okay. etc., etc. Okay. So another aspect I've actually mentioned it, but let's talk about it a little bit more. Is trend estimation. Okay, so this is less popular, but people will also do this. If there's clearly a trend that you can actually estimate out of it. So if your time series 60, let's say, is there is actually a clear polynomial trend. Usually, the linear trend people will do this. So let's say if you have data xt and you suspect that clearly there's a polynomial trend of order d. So the d degree polynomial is right there in the definition of xt. So how can we do about that? Now remember last lecture we talked about, try to remove this d degree polynomial by taking d for the difference, right? D for the difference will remove completely the d for the degree polynomial. But here, maybe actually we can use maybe least square estimation to estimate this polynomial trend. So how to practically do this? So this is basically going back to undergraduate least square estimation. So you put your data in one column, and then you put your equation on another side. So x1, if you put t equals 1, what happens? So it's the sum of the alphas, right? So it's basically something like this. And it's alpha naught, alpha 1, all the way up to alpha d. So d degree polynomial, that d plus 1 parameters. Now how about if you put t equals 2? T equals 2 here, right? Well, this is 1, and then this is 2, and then d 2 to the squared, and then in the end to the power d, something like that, right? Etc., etc. So it's 1, and then t squared, and then up to t to the power d. So writing multiple equations into matrix form, this is, as you can see, we have done this numerous times already. Okay, so if this is not really a familiar technique to you, so you need to grasp it, okay, in various situations. So you need to be able to write linear equations like this, okay, which is true for different time points, okay, so be it you walk equations and equations like this into a matrix form equation. So this is matrix form because this is what? This is, well, you can say this is a factor of x, and then you can say this is a big design matrix x. Let's use beta to denote the factor of coefficients, and then this is w. So this is noise, right? So the whole system becomes x equals to big X times beta plus the noise factor w. So if you use least square estimation, you should know the answer. So minimize x minus x beta squared. So later on you need to be able to derive the least square estimator anyway. So I'll not talk about it here, but for now, remember the answer to this is the least square estimator, which has this form, okay? So x transpose x inverse x transpose times the response factor x. So that's the formula. So of course, we basically assume x is of full rank. X is of full rank, then x transpose x is of full rank. So a full rank matrix, then it is invertible. Okay. So there's all the chance in the world that x transpose x is not invertible. For instance, if your dimension here, what's the dimension here is d plus 1, right? The dimension of this problem is d plus 1. There's d plus 1 parameters here. So if your d plus 1 is actually larger than capital T, so dimension larger than the sample size, then least square estimator will not exist, okay? Will not exist. Because x is automatically not of full rank. X transpose x will automatically be not of full rank. But assume it's of full rank, then we can estimate our w hat equals to what? Equal to xt minus alpha naught hat minus alpha 1 hat t, etc., etc. Alpha d hat t to the power d. Okay. So what we hope the estimated non-series WT hat is stationary, so you can look at this plot, right? Or look at the ACF of this WT hat, does it look stationary, etc., etc. So that's one thing I actually wanted to talk about, and I don't have time in the last lecture. So the important thing is most people actually do elimination rather than estimation of the trend. So like last lecture, they use difference operator. In the case study, you also use difference operator to make certain trend or seasonality disappear in the house price data, okay? So it's really important to look at the within week exercise as well. But trend estimation, some people also do it. If they are confident, they have a linear trend, etc. Okay. So they want to obtain information from the trend as well sometimes. So they estimate it. Alright? Any questions? So this is just least square setup basically. Okay. Let me know if later you have any questions. Okay. So the next thing I want to talk about is something more important related to what we have done in the last lecture. Now in the last lecture I said, why do we look at ACF and PACF in the first place? Well, because we want to see if, first of all, if your data looks like an AR model or an MA model. So if it's an AR model, then the PACF should look like there's a cutoff, okay, the empirical PACF. If it's an MA model, then the empirical ACF should have a cutoff, okay. If it's an ARMA model, then it's a little bit more complicated. Usually both ACF and PACF exhibit some kind of exponential decay, but not cut off immediately. Then you suspect that maybe is an ARMA model. But how to determine the order? Okay, so it's a really practical question. Well, if you look at some textbooks, there's something called a generalized ACF or generalized PACF, which I'm really hesitant to teach you guys because they are restricted usage. Okay, restricted in terms of theoretical requirement as well as practically people don't use that much. What people usually do instead is consider different models, okay? So you can use ACF and PACF, the empirical version, of course, for the data. To roughly determine the order of differences in delta to the power d or delta s to the power d, okay? So if your model if model is something like this, okay, so what is this? So this is called seasonal arrangement, okay? So just introduce to you here, together with model selection. So it should be written as something like this, okay? So phi p to the power s phi b applied on sorry, this is should be capital D. So the form is a little bit complicated, but let me explain in a minute. So it's alpha plus c to the q to the b to the s, and theta be applied on epsilon t, where your epsilon t is white noise, again with mean, zero, and variance in the square. So what is this? So if you think about it, so last time we talked about elimination of seasonality and trend, right? So here, your time series has maybe a certain seasonality equal to S here. But at the same time, there may be some polynomial trend, okay? So here, the polynomial trend can have a degree equals to d, little d plus big D plus 1. Remember, the delta S here actually, d, little d plus big D, okay? Remember, so seasonal difference also can remove a polynomial trend, okay? So this here can remove seasonality and degree d plus d polynomial. Okay? So after removing seasonality and certain trend, perhaps it becomes stationary, then you can use our model to try to make it work, okay? So remember we talked about void decomposition, right? So after removing any deterministic trend, etc., seasonality, so perhaps what remains is our model. But wait, what about this phi p and theta q here? What are they? So why not just like our model? You have only phi as the AR characteristic, theta as the MA characteristics. What is this phi p and theta q? Well, if you have removed seasonality using this seasonal difference on top of just the usual difference to remove polynomial degree, then you could have created artificial seasonality in the noise. Imagine if xt is only white noise, now you remove seasonality, remove trend, which is not there. Actually, the white noise so if epsilon t is white noise, the transformed white noise can exhibit seasonality. Albeit maybe not strong. I think I will have an exercise later, maybe next week, to actually let you really visualize that. Okay, so white noise, after making this kind of transformation, you calculate this KCVS again, so then you see that seasonality emerges. Okay, something like that. Okay, so after.
So is the second loss for this, it can exclude seasonality?
Yeah, can exhibit seasonality. So imagine there's a white noise within xt. If you do this kind of transformation, then you actually artificially created certain seasonality as well. If you don't model that, well, then your modeling may fail. Okay, so in order to try to model that as well, so this comes in. They are there explicitly for modeling the seasonality in the form of an AR and MA characteristic polynomial. So what are they? So let me give you some terminology. So this is phi p here. As a polynomial in z to the power s is 1 minus, let's say phi 1 z to the power s minus up to phi p z to the power big P times little s. So it's a high degree polynomial, so this is called the seasonal AR characteristic polynomial. Okay. And by the same token, so theta big Q z to the power s is 1 plus theta 1 z to the power s plus up to theta q big Q z to the power q qs. So this is seasonal MA characteristic polynomial. Okay. So seasonality, the original xt can be strong. Now after doing removal of seasonality and trend, there can still be weak seasonality artificially injected into your transform data, because there could be something like white noise in xt itself. After you transform it like this, then artificially you create seasonality. So in the end, you need to model that as well. That's why the seasonal ARIMA model comes in this form. Okay. So I think I'd better talk about this I here. I means integrated. Integrated means well, you need to take difference in order to make it stationary. Okay. So integrated means this time series linear combination of them can actually be I mean, the time series themselves can actually be non-stationary, first of all, so they could exhibit time trend. But linear combination of them can become stationary again, so like this, okay? So this is exactly how we model the integrated time series, okay? So maybe certain linear combination after taking differences, seasonal difference, can become stationary again. So we call this XT itself integrated. Okay. So people would consider this kind of seasonal Riemann model in this general form, and then try to think, okay, first of all, how to look at D, little d and big d, so to make it look more stationary without any seasonality. Okay, so that's what I'm talking about. So in the first sentence, so here you can try to look at ACF and PACF to see roughly the order of difference that you need to make XT look more stationary. Okay, so I guess I will do a little bit of the London house price data exercise with you together, just a little bit to demonstrate this point. Okay, but let me continue with what I need to introduce first. Okay, so it's not the end of the introduction. So the phi and theta are usual AR and MA characteristic polynomials respectively. And how people do model selection, this is after all model selection. So model selection for this type of complicated seasonal model, seasonal Riemann model. So how people do this? Well, this is also another reason I don't introduce that generalized ACF, PACF. Okay, so in this kind of seasonal model, they don't work anyway. Okay, so people instead define something called a high key information criterion. If you have done your undergraduate statistics, you must know this. Time series models, same kind of definition. So it's -2 times the maximized log likelihood of the data plus 2 times m. Okay, now what is m? M is the number, so the hash is the number of parameters in the model. Now that includes sigma square. Okay, sigma square is also one unknown parameter. So this should be, now if you look back at the model itself, how many parameters are there? Okay, so, well, if you look at the AR and MA characteristic polynomials, both the seasonal and non-seasonal version. Now, in the seasonal AR characteristic polynomial, how many parameters are there? There are big P number of parameters, right? In the usual AR characteristic, so there's a little p. In the big seasonal MA characteristic polynomial, there are q parameters, big theta 1 up to big theta q. And also the usual MA characteristic polynomial is little theta 1 up to little theta q. So there's little q. And then of course there's a sigma square. So that's the number of parameters, okay? So you can say the dimension of the problem, basically. So people call this kind of model again is seasonal Riemann. So the full name seasonal autoregressive integrated moving average model, right? So for the non-seasonal order means the non-seasonal AR and MA characteristic polynomial, they all have order P and Q respectively. And the number of difference you use is a little d. and multiply with the big P, big D, and big Q sub S. Okay, so S is the seasonality, and this big P is the order of the seasonal MA characteristic polynomial. Big Q is the seasonal MA characteristic polynomial. So big P is seasonal AR, big Q is seasonal MA order. The big D is the number of seasonal, the order of the seasonal difference. Usually, with the vast majority of time series modeling, so usually this big D is at most 1, usually. Okay. To be honest, I've never seen anything useful larger than 1, to be honest. So usually it's either 0 or either 1. That's the usual case for vast majority of practical data. This little d on the other hand, this could be integrated. So if you have a really high degree polynomial trend, then maybe you need higher d to eliminate that. So what is this AIC? Well, you talk about log likelihood. Hey, if it's just white noise, then how can you talk about likelihood? Okay, so usually in R, if we talk about AIC, usually, well, they assume Gaussian white noise. Okay, so you have a distribution for the noise. And remember in the last lecture, how can we utilize the Gaussian information? Well, we look at the likelihood of the data as a product, right? Product of conditional densities. Okay, so the same here. Okay, the log likelihood is the log of that product of conditional density. So it's a sum of log conditional densities. Okay, so that's exactly how R handle this. All right. So they try to maximize that log likelihood, multiply by -2 and then plus 2 times this number. That's exactly the AIC that you get, and the formula in R. So how to determine? That comes back to our most important question: how to determine this little b, p, big P, little q, big Q? Well, you want to find model such that AIC is minimized. AIC is minimized. So we want to minimize the AIC. And this comes back to the trade-off between goodness of fit and complexity. So complexity of the model itself. Why is that? Why is there a trade-off? Well, if you look at the formula for the AIC at the top, so if you want to minimize the log likelihood, minimize the AIC, then you need to maximize the log likelihood, right? So to maximize it, is a minus sign or on the left-hand side. So maximize log likelihood means you're minimizing the left-hand parts here. The more parameter you put in the equation, in the seasonal Riemann model, the larger the log likelihood in general. Even if you put in rubbish parameters, the log likelihood will increase. Albeit maybe increase just by a tiny amount. Okay? But if you put in large number of rubbish parameters, then this term may explode. Okay? So you're basically penalizing overcomplicated but not useful model. Okay? So it has to be complicated enough so that the log likelihood is maximized. At the same time, it cannot contain too many rubbish parameters, not useful in explaining the data, so that this term will not be too large. So in the end, this AIC will be basically trading off between goodness of fit and complexity of the model. Okay, but if you question, so why -2? Why not -3? 1 minus 2.5. Here minus 2.5, 2.1. Okay. So these numbers actually is related to the linear regression modeling when they calculate the expectation of the residual sum of square. Okay. So these numbers actually comes up naturally. In time series context, so they basically extend that theory. Okay. But I'm not going to talk about that. Okay. So if you have heard something called model CP, so that's related to these why these numbers, y minus 3, y minus 4, etc., etc. Okay. The most important thing is so you know this formula of the AIC automatically will induce trade-off between goodness of fit and complexity of the model. All right. So let's let me see how much time. Good. So let's so this is actually the reading weight exercise, the case study. So let me go through it a little bit to demonstrate that concept. So where to download the London house price data is here, just below COVID-19. Okay. And then there's actually the scripts. So you can actually download the scripts. Okay. So I've actually done the scripts. But at least try to understand, okay? What? Okay. So I'm really can make this larger. This work again.
Oh, it's on. No, it's still very.
Oh, that's good. Thank you. Goodness. Okay. Let me make this larger here. Okay. Okay, doesn't matter. Let me copy it into first. So I hope this is large enough for you to see. Maybe not. So let me make it even larger. So I hope this is large enough. So basically, we need to read in the data first. So data is here. Oh no. Okay. So the data, I hope I have demonstrated to you. So this is the London house price data. So if you look at the data itself, then of course you can see that starting with 1995, okay, this is monthly data. So it's up to August last year, okay, when I prepared the materials. Okay, so you can see it basically going up quite nicely. So not exactly a linear trend, but perhaps some local polynomial trend, but overall it's basically maybe a linear trend, or at most a quadratic trend will be enough. So any nuance maybe can be left to the noise to handle. So at the end of the day, so you can see it's basically there's a linear trend, but it's a monthly data, as I talked to you just now. So is there seasonality going on? So we have to suspect it will be seasonal with that s equals to 12, because this is a monthly data, okay? So for every monthly data, you should really think about that first. So how to visualize that? How to actually show that is the case? This is the return of the house price data. So it certainly looks more stationary return, because return basically is the difference, right? Difference of log return. And it's the ACF and PACF. Okay, so the ACF. This is for the return series. So for the return series, it certainly looks approximately okay, but for the ACF it's still not okay. So let's look at the ACF for the original series. Okay, so ACF2 of okay. So let's look at the ACF2 of the original log house price data. So I take logarithm as a scale. So that's what I want to demonstrate to you, okay? So you can see immediately, so the only conclusion you can conclude from this ACF is, okay, it's not stationary. Now these many stakes that stick out from the blue dotted band, they can alternate in sign, so very positive, very negative, and then very positive again. They can alternate in sign, no problem, but the main point is after many, many lags. So this is not 1, 2, 3, 4, this is 4 years, okay? So 4 years means 48th lag. So lag 48 is still sticking out very consistently. The reason is, well, you have a linear trend basically. Try to plot time series with linear trend and then plot this ACF. It's all like that. So just looking at the ACF, okay, well, there's a certain trend going on, of course. It's not stationary. So what's next? Of course, take difference maybe. Well, the return is basically difference of the log return, okay? So if you look at the return here, return equals to the difference of the log of house price. So I hope in this lecture, in the latter part of the lecture, I'm going to talk about this log return in a more systematic manner when I talk about Gauge and Arch model. Okay? So return is the difference of log return. Okay? Log house price. So difference of the house price, of course, then you basically remove a trend. At least you remove a linear trend. Okay? So return, you expect, okay, after removing the linear trend, what is the plot then? So that's ACF to return. Again, so as expected, after you remove the linear trend, return basically is removing linear trend, is first order difference. So of course it looks more stationary, but is it actually that stationary? Well, could be. Could be. But if you look at the number of lags there, if you look at the number of lags there, so up to 4, well, it still sticks out, but well, it is decreasing in magnitude. But up to 4 years, there's still lags, okay? And in between the years, well, there's not much. So what is this phenomenon? This phenomenon is seasonality, okay? So it's a monthly data after all. And if you think about the house price, well, people may buy in the summer rather than in winter. So there are more sales in the summertime, when more sunshine, okay? Something like that, okay? So monthly data usually have a seasonality equals to 12. And this shows, okay? This shows. So at all yearly lag, it sticks out. Okay? So this is a practical sign that, okay, there's seasonal. Perhaps I need to apply seasonal difference as well. Okay? But is it strong enough? I don't know. Well, this is marginal. So some of this, sometimes after we move a trend, polynomial trend, so at yearly difference, so we stick out like a sore thumb. So here it sticks out, but not very, very, very strong. Okay? So perhaps you can continue to make a seasonal difference as well, which is what I suggested in the question actually. So the series first order difference, so we have done that, right? And then second order difference maybe, so perhaps looking at this ACF, maybe you want to make a second order difference, a seasonal difference actually. And how to make seasonal difference, by the way? Well, the return is first order difference. So you may define V equals to difference of return plus seasonal difference, seasonality equals to 12, okay? So that's seasonal difference. Now look at HCF2 again for the seasonal difference return. See all the states that's coming out at yearly order, so they disappear. At least disappear in large lags, in large yearly lags. So at lag 1, so still stick out. And that is to be expected because even if you take seasonal difference over white noise, so you will artificially make seasonality. But all those stronger seasonality, well, they are cut out. They are removed. You artificially injected weaker seasonality, but removing very strong seasonality. Okay? That's what you're doing. So in the end, okay, perhaps this time series now can be modeled by our seasonal ARIMA model. Okay? So that's the idea, alright? So it's all practical. It's all practical here, okay? Which follows the what we have talked about. And you may also how then I look at find a suitable seasonal ARIMA model. So what order do we look at? Well, perhaps people usually look at a certain different order. Okay, so in ours there's a automatic flip. So there's something called auto.arima. So if you want to look at how this works, then you can So I can't remember auto.arima. It may be in forecast, maybe in one more. I don't know. Okay, but auto.arima. So that's the yeah, it's in forecast. So people usually use this to try to find base model first, And then after finding the base model, so altogether, remember, let's say V, okay? Let's say this fit dot V equals to this. So what do you think will happen? So if you summarize fit dot V, so that's the fit, okay? So we'll give you exactly, see the seasonal RIMA, little p equals to 2, little d equals to 0, little q equals to 2, big P is 0, D is 0, but big Q is 1, okay? So a seasonal RIMA model with the usual AR coefficient equals to 1, so phi 1 equals to 1.05, phi 2 equals to minus 0.18, and then theta 1 minus 1.15, theta 2 0.54, and then big theta 1, this is seasonal MA1, okay? This is the big theta 1, is minus 0.87, okay? So people usually go from here and try to find different models, so not too far away from this automatic fit. That will minimize this AIC, okay? So let's focus on this AIC also. You may ask, what is this AICC? What is this BIC? So I'm not going to talk about that in this course, okay? So we'll focus this on AIC. There are other penalization measures, as you can imagine, okay? So it's basically this, okay? And, well, is it good? Okay, so people usually do some diagnostic plot. STS done, okay. So this diagnostic plot is something that we'll talk about actually. So plot the standardized residual of the model after fitting this seasonal RIMA model. And then look at the residual. Remember, this fit, all of this R fit will assume the silence, a Gaussian white noise. So the very least is to see if the ACF of these white residuals look like a white noise, okay? And then at the bottom, so p-values for the Young box statistic. I will talk about that in a minute actually. So standardized residual usually, well, in your undergraduate studies, so usually not bigger than -3 and 3. So if it's outside, and that may be a problem. So it still applies here. And you hopefully do not see any trend. So do you see any trend? Clusters of negative and positive residuals. There you go. So there's a cluster of negative residuals here. It's not good, okay? So perhaps we can do better by finding some other order of seasonal RIMA model that may have a better fit, okay? This one I'm not going to talk to you about. Rather, I'll ask you to look at the lecture note. Where is it? So in the lecture note, this is laid out in here, model selection and diagnostics. That should be a practical. What is it? I think I depend solely on the scripts. So you can see that in this script there are a lot more. Have a read of the lecture note, of course. Okay, on the is 3.6. At the same time, so the script that I've provided for the London House Price case study, so it basically teach you through what kind of commands to use to feed a model, okay, etc., etc. Okay, so all the practical knowledge is in here. All right. So have a look at the read and read exercise. So we'll talk about that in the seminar as well. All right. Okay. So I hope this gives you some idea on this practical side of the model selection. After introducing the most general, the seasonal remote model. Okay. So I'll give you 5 minutes break, and then when you come back, we'll talk about this diagnostic problems. Okay. Before I go to financial time series. All right. So please come back after 107. Okay. I'm really sorry. Yeah. Just make it in time to come to I'm stuck. Yeah, yeah. Is it too difficult? Okay. Oh, okay, okay. So you basically use this kind of coordinate. Yeah. As long as you can fit that. So at this stage, does this resolve the identification issue?
Yeah, I thought it solved it. Like, it kind of like that's the first time.
Well, if you can theoretically prove it, I think it should solve the identification issue. Have you tried empirically?
Yeah, I tried
Get
empirically.
back.
I did silly mistake again, but
It's okay. It's okay. If you so try to do all the empirical things first. Okay. So if you want to find a proof, you can. After term break.
I've had class every day. Except yesterday. Only mess.
You mean
I know. I guess.
Well,
That doesn't sound good. It's fun then, but
I saw you instrumental variables.
full term.
How? You ordered.
Okay, so you assume the XT is don't have the strong capacity of the what now we should have. Yes,
Is this not at 12?
that's okay. That's okay.
I can control.
What?
This is
I'm about to put it in.
solid.
Sure. You just said original after the original.
Okay. Come on. Just here. No. Seasonal. Whatever.
Okay, so let's get back to the lecture. Now, the diagnostic plot. So ACF residual, I've explained that. Standardized residual, so it's basically residual divided by its variance, a square root of the variance. So not came very good, but what is the Young-Box statistic? So I'm going to introduce that. Okay, so it's just very it doesn't work. Wait, but in the meantime. Wow. Okay. So the next thing I want to talk about is the Young-Box statistic. And some people call it the Young-Box PS statistic. So in textbook you see LBP statistic. So this is it, the Young-Box PS statistic. And the LBP test associated is actually for testing white noise. So they call it testing for whiteness over time series. By the lengths, okay. So this kind of white noise test, so people are still doing that, okay. So I have a paper on this with high dimensional white noise, and people are improving that even nowadays. So this is a more traditional one. So the statistic involved is this Q star. This Q star is defined as your some adjustments using the sample size to t times t plus 2. The main thing is you look at the fitted ACF, rho j hat. You square them and then you will sum the adjusted value of them. Okay, so we readjust it by 1 over t minus j for some reason. Okay. And what is k? K is the number of lags considered. So it's usually predetermined. So if you look back at that Young-Bon statistic, okay, so the y-axis is actually p-value, okay? So how do you get p-value of these kind of statistics? Because of this approximately asymptotic result, so it's going to chi-square m, chi-square k minus m, m is the number of parameters fitted. So you will go to a chi-square k minus m under your null hypothesis that the data at hand is white noise. Of course, the alternative hypothesis is okay, it's not white noise. So if data gives you Q star hat as the value, of course for a fixed value of k, right? K is determined. Then the p-value of the test using the chi-square approximation here, you can see this is exactly chi-square approximation, so p-value of the test is approximately basically a chi-square k minus m is larger than or equals to this value Q hat star, right? So basically this p-value is under h naught, okay? If it looks like a white noise, then you will expect Q star hat is not too large, okay? Then the p-value will be large. But if it's not, if it's a white noise, okay, sorry. If it's a white noise, then your Q star hat shouldn't be too large, okay? So if it's a white noise, all the rho j hat should be small. Look at it, they start from j equals to 1. So rho 1 hat, rho 2 hat, they all should be, well, theoretically speaking, they should be 0 if they're white noise, but it's empirical. So they something there, but shouldn't be too large. So this Q star hat shouldn't be too large if it's a white noise. Then probability of chi-square k minus m larger than something not too large, that this probability should be large, okay? So this is the p-value. So if h naught is true, then we expect this p-value to be large. On the other hand, if it's not a white noise, then this rho j hat should be something that is substantially larger than 0. Then this Q star hat should be large. So probability that it chi-square k minus m larger than something that is unexpectedly large, of course, is small. So this probability will be small. Okay. So if it's very, very different from white noise, then you will expect these p-values to be extremely small. All right? So that's what you see. And in that fit, you should see that so those p-values are not really that small. Okay? So they're all much bigger than 5%. Okay? So the fit, diagnostically, it looks like white noise at least. Okay? But as I said, the fit can be improved, perhaps if you can make the clustering of residuals disappear. As I explained, there's a group of clustered negative residuals, right? So it really, that part at least, the residuals doesn't really appear to be behaving randomly, right? That's clustered of negative residuals. Okay, so that's the box at this stage, and that basically is the conclusion of this model selection topic. So all other practicalities, please look at the scripts corresponding to the London House Prize case study. Okay. And from here on, so we'll move to the financial statistics, at least this half of the lecture, and maybe the next half as well, in the next lecture. So, before that, so I think I want to introduce something I missed out. And I hope you have checked it on the lecture notes. So in exercise 5, there you can see there's absolute summability that appears in one of the last questions. So what is absolute summability? If xt can be written as an MA infinity, like this. So you have silent t is white noise. It's just a definition. So we say xt is absolutely summable. If the sum of the absolute value of the MA coefficients in this MA infinity representation is actually finite, okay? So that's absolute summable means the coefficients in MA infinity. So it's a very simple definition, but there's certain conclusion. So if xt is actually absolutely summable, then xt is stationary. I think I provided a proof in the lecture note as well, so try to do this as well as some kind of exercise. And in the latest exercise, I also have demonstrated that absolute summability is not necessary for stationarity. So the relation is, so if you have an absolutely summable time series, then it is stationary. But does stationarity certainly means it's absolutely summable? Well, not the case. In the latest exercise, the last question, so I demonstrated to use something called harmonic time series, right? So that time series, okay, is stationary, but the coefficient is not absolutely summable, okay? So that's the relation, and so this is something I missed out, so I just want to add it. I hope you have checked it on the lecture note as well. So I'll move to financial time series now. So that's something that we need to talk deeper. So for financial time series, it will be one lecture, I think, before we move to multivariate. So usually when people talk about financial time series, they don't refer to the London house price data that we talked about. So basically talk about really financial price data or financial return data. And usually they have certain characteristics, but I'm not going to talk about that. This is not financial statistics. So the data can have no normal distribution. No normal means it has larger kurtosis than normal. Normal distribution has kurtosis equals to 3. Okay, so larger means larger than 3. And another prominent feature is volatility clustering. So I will explain all this. So return look like a white noise. But not the square return. So this one I think I have demonstrated in one of the seminars, but I'll demonstrate it anyway later on. So let's fix notation. So if PT is the closing price, so we usually deal with daily closing, monthly closing. So let's think about daily closing price, okay? So PT is the daily closing price. At time t, so here t is basically daily time, okay? Day 1, day 2, etc. Or the return then is RT, which people define as not just the usual return, but they talk about log return. So it's log of the price today minus log of the price yesterday. So in the house price data, I use log return. Okay, I take log of the price and then take difference of the log price. That is the log return. Okay. So this is exactly equal to log of PT divided by PT minus 1. And you may ask, so how is it related to the usual return? You define return like this, right? Remember, the new price minus yesterday's price divided by yesterday's price multiplied by 100, right? That's the percentage change. How is it related to log return? Well, they are similar. If this is small, okay? So if the real change is small, the real return here, the ratio of price minus 1, so that's a real return, right? Real return is more than this log return and the real return. They are very, very similar actually. Okay? So this is down to Taylor's expansion basically. So try to do that, okay? Let me give you a hint. So log 1 plus x is close to x plus something, okay? So when x is small. So basically, log 1 plus x has the first term in the Taylor's expansion at x. When x is small. That's what I'm saying, okay? All right. So I've outlined several properties. Now, some properties are more involved than others, so we'll concentrate on several of them. But there are some properties that I will just talk about in the passing. There are some properties of volatility. So what is volatility, by the way? Volatility. So this definition is, of course, you need to know. So sigma t is defined as the square root of variance. Well, that much is obvious, but this variance is conditional. In finance, everything is conditional on whatever information you have up to the current time. Okay? So your Fs here is information up to time S. Okay? So if you studied stochastic process, so this information is basically sigma algebra generated by the random variables at hand. Okay? So if you don't know what I'm talking about, fine. Okay? Remember, it's information up to a certain time. Okay? So the first one, so I've talked about that. So that is the one that will dig deep. So volatility clustering. And certain other properties that leads us to the model that we're going to introduce in a minute. So we'll assume that the sigma t is at least bounded and they're continuous. And there's a leverage effect. This leverage effect is something I want to talk about. This is not financial statistics again, but well, basically stem from reaction to negative news. It's very different to reaction from positive news. So reaction to minus 5% of a stock is different from reaction to plus 5% of that stock. Okay, so that basically is the leverage effect. Investors are more conservative. Okay. So minus 5, okay, I have to sell it. Plus 5, it's fine. Something like that. Okay. Okay. So what are we going to study here? Well, the main thing is this volatility clustering. At least in this course, okay. So there are many other models that try to take care of these effects observed. Okay. So we will introduce a model that try to capture this volatility. We observe volatility clustering, and I hope. So let me quickly demonstrate what I'm talking about volatility clustering. Of course, yeah. I hope it's installed. There you go. So let's get Microsoft. Okay. Yeah, and then we can. So if you plot the, so I think I've demonstrated this to you. like this. Okay. So I think I've demonstrated to you something like this. So I can download immediately Microsoft stock price up to, I think up to yesterday, and then so this is daily closing price, and then I can ask the graph to chart it. There's 6 columns, so the adjusted price is what we're looking at. So the 6th column. So let's look at the first 2 rows. Again. Okay, so you can see that it's open OHLC price, so open price, highest in the day, lowest in the day. The closing price is what we're looking at, but there's stock split. I'm not going to explain too much, so if the stock splits, then the price will suddenly drop by 50%, so artificial, okay, so we don't want that. So we look at adjusted price instead. So all the price adjusted for these kind of artificial activities, okay, stock split. So you can see, so adjusted price is like this. Okay, so that's the price that we're looking at. And then so we want to look at the lot price. So of course we'll look at so this is 6th column. The 5th column is the volume traded in a day. So that's the lot price. And if you just plot the lot price, then you'll get the same, basically same graph, right? Something like this. Okay. So return R is then the difference of the lot price. So you plot the return R, so that's the return. So, and what is volatility clustering? This is Microsoft price from 2007. Okay, up to yesterday. So what is volatility clustering? Well, if you look at, for instance, this part in 2008, now volatility, remember, is basically the magnitude of fluctuation. Whenever we talk about sigma t, variance of the return and the square root, okay, so this is basically the larger the variance, the larger the fluctuation, okay? The magnitude of fluctuation, okay? So magnitude of fluctuation, look at this 2008, so this is July 2008. Well, basically up to the next year, okay? So you can see that the magnitude of fluctuation is quite large. And it's persistent for over a year, basically. This is over a year. And then afterwards, so let's look at, say, 2010. Well, the magnitude of fluctuation then is very small and is persistent up to maybe 2014 until there's certain large fluctuations. Now let's look at other periods. Let's look at COVID period, okay, 2020. This is around March 2020. Well, magnitude of fluctuation again suddenly increased and its persistence for maybe at least several months until it dies down. And after it dies down, it stays small. Look at this period. It stays small actually for over a year again. Okay? So all this clustering of large or small fluctuations, so we call it volatility clustering. Okay? So you can imagine volatility can sometimes, maybe it can be random, right? Sometimes it's large, sometimes it's small. But it definitely is not like that, right? Large magnitude tends to cluster together in one period, and small magnitude tends to cluster together in another period. And they're quite persistent in their clustering length, okay? So we call this volatility clustering, and we call this a persistence of this volatility. Okay, so large value clustered together for a long time, small value clustered together for a long time. So they're persistence. So that's what's volatility clustering. That's the first thing we see basically when we plot this return data. Okay. So how do people try to model this? That's all the need to be able to model this. If we can't even model this volatility, there's not many things can work, basically. This is a very basic task, okay, for a financial analyst, statistician, etc. Okay. So how do people at least model this volatility clustering? So Robert Engel come up with this arch model, so you may have heard of it already. So still active in research. Okay, so this is called autoregressive conditional heteroscedastic model. So AR is autoregressive, CH conditional heteroscedasticity. So heteroscedastic certainly means at different time the volatility can change over time. Okay, so heteroscedastic, and it's conditional to past information as well. That heteroscedasticity. Okay, so what is this model? So if XT follow this AR's arch P model. So this arch model has an order, and you need to remember the form. So xt then follows a white noise multiplied with a sigma t, and this white noise is not just white noise; it's IID white noise. People usually assume, at least in R, is assume IID normal. Okay, so it's Gaussian white noise. Gaussian standard white noise. But what is sigma t? Well, sigma t is a formula. Sigma t is this: a0 plus a1 xt minus 1 squared plus all the way up to ap xt minus p squared. Where your constant a0 has to be larger than 0, and all the other coefficients are at least non-negative. And for the order of the arch model, so AP has to be larger than 0. Okay. So that's the arch model, arch P model. Let's immediately, very quickly, look at some very basic properties. Okay. So for instance, expectation of xt is what? So I'll throw in exercises, don't worry. You need to practice that anyway. So expectation of xt, well, is expectation of xt is sigma t multiplied with your IID white noise epsilon t. Now, your epsilon t is IID, okay? And your sigma t is, does it depend on any time? Well, it depends on information actually up to only t minus 1. Look at the formula for sigma t. Sigma t is defined up to xt minus 1. So we call sigma t what? Remember, in void decomposition, we introduced that term, deterministic. Sigma t is deterministic, actually, because with information up to t minus 1, we already know the value of it. And with deterministic sigma t, of course, it will be independent of epsilon t, which is IID white noise. So it's expectation of sigma t times expectation of epsilon t, then of course it is 0. Okay. So this is a basic argument. Okay. So we'll use it again and again. Now, how about the any autocovariance of characteristics? Well, if you consider lag h larger than 0, and then consider xt and xt plus h, what do you have? Well, Mean is 0, good. So covariance is just expectational product. So this expectational product, well, for all these kind of calculation, okay, so usually people will just try to expand the variable that has the most positive time point. Here, t plus h is the most positive, the largest time point. So let's expand that. Xt plus h equals to sigma t plus h times epsilon t plus h. Well, then the same kind of argument applies. Let me write that first. So it's xt times sigma t plus h multiplied with expectation of epsilon t plus h. Why is that? Sigma t plus h is deterministic, determined up to time t plus h minus 1. Xt, of course, is only up to time t. So xt times sigma t plus h is a random variable which is determined up to t plus h minus 1. And any kind of these random variables, of course, will be independent of epsilon t plus h, which is IID. Okay? So of course, then this is 0. So good, look like white noise. Look like white noise already. Okay? So if we can indeed show that if we can show that variance of xt is actually finite and time independent, I will give you a question for that, okay, in exercise. So if variance is also time independent and finite, then xt of course is a white noise. Okay. So the more complicated time consuming is actually the variance here, not the covariances. Covariances, you see just one line and you can prove it as 0. So if you assume that, so let me go on to introduce a little bit more. How about the variance of xt? Well, the variance of xt is expectation of xt squared. The mean is 0, remember? And this is expectation of sigma t squared times epsilon t squared. And the same argument applies, so this is expectation of sigma t squared multiplied with expectation of epsilon t squared. They're independent. And epsilon t squared, of course, has expectation equals to 1, is IRD normal. So ultimately, this is just expectation of sigma t squared. Okay? And using the formula for sigma t squared, so this is a0 plus a1, expectation of xt minus 1 squared, plus all the way up to ap times expectation of xt minus p squared. So that's the formula, and for instance, if p equals 1, then what you have is expectation of xt squared equals to a0 plus a1 times expectation of xt minus 1 squared. So this is a difference equation. So you have encountered it in the last exercise. Okay, so you can try to solve it or try to expand it. So this is a0 plus a1 a0 plus a1 squared expectation of xt minus 2 squared, etc., etc. So if we iterate it m times, what you get is a1 to the m times expectation of xt minus m squared, and plus a0 sum of a1 to the power j from 0 to m minus 1. So I'm going a little bit faster, sorry about that. Now if A1 is less than 1, then if we let m goes to infinity, your expectation of xt squared will go to what? Will goes to a0 times the sum of a1 squared, a1 to the power of j, which is a0 divided by 1 minus a1. So your expectation of xt squared, the variance now is finite and time independent. Okay? So therefore, for arch 1 model, if A1 is less than 1, then you have a white noise. And in general, for arch P, we're talking about arch P, so if the sum of the AI, I from 1 to P, is less than 1, then xt is actually a white noise. Of course, that implies that xt is stationary. It's a white noise with variance of xt equals to a0 divided by 1 minus the sum of the ai from 1 to p. So that's the variance. So far so good. So if you look at the ACF of the noise, then it does look like a white noise. But I'll demonstrate it together with the next observation, okay? Which I mentioned in the passing, that return look like white noise, but squared return is not a white noise. Remember, we're talking about arch P model here. So for instance, for example, xt equals to sigma t epsilon t, and then sigma t squared is a0 plus a1. So in arch 1 model, epsilon t is ID Gaussian white noise. Now for this arch 1 model, let's consider the covariance between xt plus 1 squared and xt squared, okay? So it equals to the covariance. Let's expand the variable that is having a more positive index, time index. Let's not expand xt first. So this is it. Then this equals to expectation of product of everything. And then minus the individual products, okay? An expectation of sigma t plus 1 squared and epsilon t plus 1 squared, so they can be separated, right? They're independent of each other. And then multiply with expectation of xt squared. Okay? So what's next then? So expectation of xt squared, sigma t plus 1 squared. Epsilon t plus 1 squared, of course, is independent of this. And then minus expectation of sigma t plus 1 squared. Epsilon t plus 1 squared. Xt squared. So all of these equals to 1, as expectation of epsilon t plus 1 squared equals to 1, so in the end this is just expectation of sigma t plus 1 squared xt squared minus expectation of sigma t plus 1 squared, expectation of xt squared, which is just covariance between sigma t plus 1 squared and xt squared, right? So why do I write this back? So because now let's expand sigma t plus 1 squared, which is a naught plus a1 x t squared. And we are taking covariance of this with xt squared. So this is what? This is just a1 times the variance of xt squared. Of course, this is not 0, right? This is larger than 0, actually. So therefore, xt squared is not a white noise. So demonstration, I'll give you 10 more seconds to try to avoid that. So I'm going to demonstrate that this is indeed the case for real data. So Arch model is kind of successful in this regard. Good. Well, we're looking at Microsoft data, right? Let's look at Microsoft, okay? So this is ACF2 of this Microsoft. Well, leg 1 doesn't really look like, but okay. That's only 0.1, that's not too large, and there's something sticking out but not too serious. So I think a formal test will pass it as white noise, okay? But if you look at the square of it, that's the ACF of the square of it. That certainly doesn't look like white noise at all. Okay, so it is not white noise. Okay, so for financial time series, so real data, the return look like white noise. Square return doesn't look like white noise. Okay, for this Arch model we just demonstrated, it has this property as well. Okay, so it's good. It's kind of good. It aligns with this what we see in real data. As well as clustering, theoretically, remember, if you look at it, what I write, the model itself, we basically will expect now if yesterday's price is large, then today's volatility will be large. Okay? And if you include Arch P, where P is large as well, so it's xt minus 1, xt minus 2. So all of these, if the last P's day's price is very large, then you expect today's volatility is large. Large volatility will produce a large price usually. So large price will cluster together. Okay, it has this cluster effect baked into the formula for for sigma t. Okay. Vice versa, small price will basically usually imply small sigma t. Small sigma t implies today's price usually will be with probability high that is small. Okay, so small price, large price clustered together has certain persistence. But it turns out that the persistence is usually not enough for real data. You see the persistence is basically for several months or even years. So large magnitude of fluctuation for years. So after 2008 Lehman Brothers collapse, after COVID-19, 2020 lockdown, they all persist for several months at least, half a year to a year. And small price also clustered for a long period of time. Arch P model really can't have that level of persistence. So we need to introduce a more persistence model, a more generalized Arch model called the Gauge model, which is the next lecture, okay? So I'll see you guys next week. For those who attend the seminar, so please stay.
don't think you can. Do you get back to taxi? Do you get back to the train spot?
Yeah.
That's so
I had like the
there's no trains like the E8. Like the listings.
oh yeah, of course. Yeah, yeah. It's a daily skull. I don't know if she was so far. No,
Yeah, yeah. Yeah, because the prices are actually saying it's
yeah.
basic.
We can do this all out. So you can see.
You can see whether we have. It's kind of free, it's kind of free. Oh,
I've
you're on that.
never been angry. I just like, it's just like,
I think it's also about it's just like just
close. Yeah, you said.
that's my son didn't even have one. I screwed it. I think I was
Like the basic one doesn't. I had like, that's like massively social access. Like data.
It's 75 grand a month. How do you? This office attendance, sorry. Thank you.
Sorry. That's
Super good.
it's really tough.
What, the deep learning? Are you guys so good about image?
No, it's not.
Oh,
Oh,
you can get image recognition. Right.
yeah, no, we're doing it for reach pictures,
But we,
but we're doing it with numerical data. So,
we'll show this,
so we have like the coefficients of reads.
oh, so you like color mapping and stuff. See here.
Thank you very much.